Welcome everyone to our latest Zero Carbon Mine webinar. We've got today we've got Peter Clifford from Paradigm Fuels, who's going to, it's quite a timely sort of discussion around renewable diesel with the situation sort of in the Middle East. So yeah, I'll basically hand it over to Peter to run through his slides. But if you've got any questions, type them in the chat sort of box, but we'll probably leave them to the end of the presentation. So yeah, I'll hand it over to you, Pete.
Oh, well, thank you very much, Brett, and a good day to everyone, and thank you for joining us. The intent of this webinar is to describe our patented technologies that allow us to affordably produce renewable diesel and also products from ethanol using a common feedstock of sweet sorghum. The plan is to give you a 30-minute presentation, then open up the meeting for question and answer. So let me put up the first slide, and so there we go. So why sweet sorghum? Well, it produces 80 tonnes of biomass per hectare per crop, and that in only 4 months of growth to maturity. And so in well-irrigated warm areas, it's possible to grow 3 crops per year. So sorghum grain is the 5th largest grain crop in the world, with maize, rice, wheat, barley production dominating, but it's a food crop. And for those living here in Australia, it's possible to go to your local Coles supermarket and buy a packet of gluten-free sorghum flour. Now, if you were to choose to produce grain from sorghum and produce 3 to 4 tonnes of grain per hectare, there will be a drop in the brix sugar content in the stalks, resulting from bringing the heads of grain to maturity, but the net loss in renewable diesel production as a result of using sorghum as a food crop is only between 4 and 9%. So sorghum is a food-friendly crop. One more point is that all of Australia's current diesel budget can be met with about 2 million hectares of crop within the available 70 million hectares of land that has rainfall between 800 and 3,000 millimetres per year here in Australia. So this would equate to 6 to 8 million tonnes of sorghum grain, which still falls far short of Australia's wheat crop of about 30 million tonnes. Okay, just as a brief synopsis of what we're capable of achieving from our process, and that's depending on the configuration. So from 2,300 hectares of sorghum crop grown in the northwest of Australia, with one configuration, we can produce 28 megalitres of renewable diesel and 32 megalitres of sustainable aviation fuel. Now, very topical in Australia is the fuel security discussion, but in this model, the farms themselves, assuming there are many such farms, will hold large tonnages of fuel that are accumulated for shipment. Now we have an ethanol train, which produces 47,000 tonnes of ethanol per year, and from which we can produce the 32 megalitres of SAF, sustainable aviation fuel. Alternatively, the ethanol can be used to produce 28,000 tonnes of ethylene gas, or a similar tonnage of bio-HDPE. Furthermore, we produce 19,000 tonnes of ammonium nitrate fertiliser, some of which we will return to the sorghum farm. And there's 104,000 Australian carbon credit units, which at $37 per ACCU is worth close to $4 million. So that's an overview, and the numbers that I quote as we head into this presentation, and for the benefit of overseas or people looking at this offline, will be in Australian dollars for 2,300 hectares of sorghum crop running 3 crops per year. Okay, to start the discussion on our technology, I first wanted to address the circularity of the system. First is the input into the system, which is the sorghum feedstock, having captured about 120 tonnes of carbon dioxide per hectare, a number that is based on molar balance calculations. And then there's the outputs, which are the ethanol products, ethylene, high-density polyethylene, sustainable aviation fuel, and or renewable diesel. And then there's lipid oil products such as renewable diesel and sustainable aviation fuel, and digestion products such as nitrogen-rich digestate, which we bury below the crop, and ammonium nitrate fertiliser. Now, the main process trains are the ethanol production, the lipid oil production, and the nitric acid production. But I'll talk about these and other components such as the anaerobic digestion and power generation, and we'll reference this particular drawing. So this is, we'll keep coming back to this, but I will talk about these and other components such as the anaerobic digestion. Okay. All right, we'll keep coming back to this. But the main point is that no gases escape from this system. All carbon dioxide is captured, so as a minimum we have a carbon net zero operation. But it's better than that. See, this diagram describes the one input and the three outputs of the process. The input is from the crop and the outputs into the ethanol product, in this case bio-HDPE, renewable diesel, and a digestate, which is then buried below the crop. The digestate is used as a feedstock for carbon farming and for the accumulation of Australian carbon credit units. In fact, 1/3 of the carbon that we capture from the sky ends up being buried below our sorghum crop. The ethanol train can produce sustainable aviation fuel, as distinct from HDPE, which is slated law as carbon net zero. But better still is that we require hundreds of thousands of tonnes of bio-HDPE for the construction of our algae growth system to produce large quantities of renewable diesel, but which we can also, but this also can be used to produce sustainable aviation fuel. And so there are two separate processes within our system that can be used to produce sustainable aviation fuel. The 32 megalitres that I quoted in a previous slide is just from the ethanol train, but can be substantially more, 26 megalitres more, making the total SAF production 58 megalitres if we were to change the process parameters to produce SAF rather than renewable diesel through the hydrotreating process. Similarly, by extending the alkalization parameters, we can produce renewable diesel from the ethanol train. In fact, we do produce renewable diesel when producing SAF, about 5% renewable diesel, which needs to be removed from the SAF product, and helps us to explain why the ASTM standard limits SAF production or SAF produced from ethanol to a 30% blend with jet fuel. You can't have renewable diesel waxing up at cold temperatures and at high altitudes. But we see a better commercial model in producing HDPE, which not only allows us to sequestrate massive tonnages of carbon dioxide, but also because we need to value add to the HDPE to create our extruded materials for the algae growth system, such as HDPE sheet and corrosion-resistant guttering, pillars, braces, and planks. This value-add product is worth far more than SAF, and it's something we have to produce anyway. So the sum product is that we have more revenue and an opportunity for long-term permanence in carbon dioxide sequestration now that we take the overall, and this will take the overall carbon credit of renewable diesel through the roof. In other words, we consume far more carbon dioxide from the atmosphere than is produced by combustion of biofuel. That is, the production of energy in a Scope 1 scenario is carbon negative. Now, I'll say that again. In producing some carbon dioxide in the burning of fuel, right? Some carbon dioxide in the burning of fuel requires a disproportionately large amount of carbon dioxide sucked from the atmosphere. Now, no other renewable technology, whether it be solar or wind, can make that claim. And this has the potential to change the way people think. From a carbon balance perspective, this drawing hasn't included the nitric acid process and production of naphtha. Otherwise, the drawing would become too busy. But if we were to include the NOx generated in the naphtha product, there would be 34.7 tonnes of carbon per hectare into the system. And I'm talking about just the carbon atom, and 34.72 tonnes of carbon per hectare out of the system. So these numbers represent a perfect balance. So let's start talking about the components of the system. Our first process is the production of ethanol, going back to that drawing. Now, this is not new, but what is new is that we are using nitric acid generated within the system as a hydrolysis agent that upon completion of pre-treatment is then neutralized with ammonia to produce ammonium nitrate salt, which is later used as a fertiliser. What we have is a hydrolysis process, which means we break apart the constituents of the biomass. And in other words, we pretend the biomass, we pre-treat the biomass to convert the starches to sugars, expose the hemicellulose and separate the cellulose from the lignins. So this we do in trenches, using much the same construction as our algae growth system, which I'll describe later. But because of the significant throughput, about 1,000 tonnes per day, and which includes a lot of water, and the fact that the entire pre-treatment and saccharification process is staggered over 6 days means that we require a lot of storage. So rather than utilising tanks, it is more affordable to use a variation of our algae system, being a trench, and all made from bio-HDPE, a product of our ethanol train. Now, saccharification uses enzymes, which breaks the cellulosic material into dissolvable sugars. And we end up with a sugar soup, which can be fermented. And therefore, we are fermenting far more sugars than what was initially in the juice. A saccharification method was studied at the Queensland University of Technology at the Mackay Renewable Biocommodities Pilot Plant, and concluded that it was theoretically possible to produce 8,130 litres of ethanol per hectare from a single crop, and with a biomass of only 60 tonnes per hectare. Whereas our modelling suggests that from 80 tonnes, not 60 tonnes per hectare, and we have 3 crops per year, it is possible to produce 27,000 litres of ethanol per hectare per year, which is far more conservative figure than the study I just mentioned. Furthermore, with high availability of internally produced ammonium nitrate fertiliser, as provided by the paradigm model, a figure of 27,000 litres looks very achievable. Now, elsewhere, studies in Brazil and the US have provided substantive information. The corn industry uses amylase enzyme to chop large starch molecules into dextrins for the manufacture of corn syrup. These enzymes are commercially available, and manufacturers' specifications for, as an example, alpha amylase enzyme is 2,000 units per gram, where 1 unit is the amount of enzymes that catalyzes a reaction of 1 micromole of substrate per minute. But, it's commercially available. Now, the anaerobic digester is a key component, and that's just there on that drawing, is a key component producing 4 useful products used within the system. There's the biomethane for gas engine power generation. There's the carbon dioxide, which is in abundance, and we use as an algae feedstock. There's ammonia for fertiliser, and there's the digester, which is buried below the crop and sequestrated for carbon credit. For 2,300 hectares of crop, the anaerobic digester processes about 185,000 tonnes a year of biomass. And of that, there's 57,000 tonnes of cellulose, 49,000 tonnes of lignins, there's 11,000 tonnes of filtration remnant, but there's 68,000 tonnes of algae remnant, which contains more than 70% carbohydrate and protein. In fact, the protein alone will be about 70%. And then there is 10% nitrogen, and this remnant sits in a nitrate soup, a total of 185,000 tonnes per year of high quality feedstock to our anaerobic digester. Okay, one of the keys to affordably produce biofuel is to produce internally our own electrical power. Now, our process consumes 15 megawatts of power, and we have 16 megawatts of excess power available for other purposes. And at $100 per megawatt hour, the 2025 annual average wholesale price for New South Wales was $103 per megawatt hour. Is $13 million per year, which is 35 cents a litre for ethanol on top of other production costs. Now, we don't have to account for that 35 cents a litre because we are producing our own power. If you were to compare against the old processes that don't include pre-treatment and saccharification, and which produce far less ethanol, then that power cost will be far greater than the 35 cents a litre. So whilst on the subject of cost saving, it is the production of our own fertiliser, which for sweet sorghum, our high biomass crop, having 2 to 3 times more biomass than that of sugarcane, is a significant cost. So the Sugar Research Australia examined the application of 140 kilograms of nitrogen per hectare near Mackay to produce 130 tonnes of sugarcane per hectare, and at $1,100 per tonne of urea and prorated by biomass, it's about another 4 cents a litre of ethanol at the cost to produce that product. And it can be much higher depending on a multitude of parameters. So I'll talk about our fertiliser production method shortly. And also we're producing twice as much power than we need, which allows us to consider desalination of water to enable 3 crops per year. Because this is a farm-based model, we eliminate transport costs, which is in Queensland for medium haul, is about $9.40 per tonne of cane. And that tonne of cane will produce 80 litres of ethanol from the extracted sucrose, the old ethanol production method, which is another 12 cents a litre. So in all, we have saved 51 cents a litre without even considering higher yields in the crop. In fact, there's a post we put up on LinkedIn that describes one of our patents that increases crop production on the east coast of Australia by 90%. Have a look at it. And one thing our process does allow for is the constant feed of biomass material to the anaerobic digester, enabled by staggered harvesting. Better said, is continuous harvesting, and a crop that only takes 120 days to grow. Though I haven't shown the accumulated gas flow generation, it is pretty much a straight line, meaning methane delivery to our gas generators is steady flow. That is very useful when considering production method and provides us with a range of production efficiencies when applied to other production components. The second process train is our algae growth system. And I mentioned earlier, we capture all carbon dioxide generated within the system. And for a 2,300 hectare crop, there's 58,000 tonnes of carbon dioxide produced by the fermentation process. There's 82,000 tonnes a year of carbon dioxide produced by the gas engine generators. There's 95,000 tonnes of carbon dioxide produced by the by the anaerobic digester, and there's 31,000 tonnes a year of carbon dioxide produced by this NOx generator. In all, 266,000 tonnes a year carbon dioxide, all fed into the algae growth system as its feedstock. And we also produce 58,000 tonnes a year of nitric acid. A lot of that nitric acid is consumed by the algae, which is 7% by weight nitrogen. I mean, nitric acid is HNO3, and H being the proton and NO3 being the nitrate. So it's the simplest form of nitrate. Okay, so we have this high concentration of nitrogen in the feed, or first of all, what happens as a result of this is that we end up with a high concentration of nitrogen in the feed of algae remnant to the anaerobic digester as digestible waste, and which is a large portion of the digester's feedstock. So we fertilise this algae with nitric acid to obtain a pH of 5.5 to 6.5, in other words, mildly acidic, which also provides just enough stress to the algae to increase the lipid oil production. And nitric acid is also used in tree treatment, which I briefly discussed, and in electrode flocculation to increase conductivity, which also is a process that produces hydrogen from the electrode flocculation, because it's a form of electrolysis. Well, why electrode flocculation? Well, it works. And algae has what they call a zeta potential of about minus 17 millivolts. And it's meant to keep the algae cells apart, but it's used by electrolysis to capture those cells. So very shortly, I'll describe this algae growth system, which is the centerpiece of our second process train, the production of renewable diesel. But first, an explanation of our nitric acid production train. This is a cross-section of a furnace containing pressurized ducts. This furnace and the internal ducts are about 15 meters long, and the gases in the ducts contain a high concentration of oxygen, given that the algae growth system consumes carbon dioxide to produce a high concentration of oxygen, which we tap into. So we mix that with air, which is 80% nitrogen. And so we have a high concentration of oxygen and nitrogen gas heated under pressure to generate NOx. Now, NOx describes a family of nitrogen oxides, NO, N2O, NO2, N2O3, N2O4, N2O5, but predominantly NO, one atom of nitrogen and one atom of oxygen, which according to Bowman's theory, there's an estimation of the amount of nitrogen oxide that's generated as a function of time at the higher reaction temperature and at a concentration and pressure of the oxygen and nitrogen. We then saturate the NOx gases with water mist and pass them through a corona discharge device, which is a high voltage device that effectively ionizes the gases, much the same way as you would see around transmission lines on a misty night. The NOx converts to nitrous acid, and as a benefit of its short half-life is that we end up with nitric acid. So we can produce the 58,000 tonnes of nitric acid per year that I mentioned in the previous slide. And before I discuss the algae growth system, I should also mention that biodiesel is not renewable diesel. Biodiesel is a fatty acid methyl ester, which is not warranted for straight-up use by major engine manufacturers. But renewable diesel is warranted and is a paraffin, a very different type of fuel. So lipid oils are extracted from the algae, and they are processed into renewable diesel using hydrogen processing technology. It's called hydrotreating, that is widely used in oil refineries. So we can produce renewable diesel at around about 22 cents a litre Australian. So I just wanted to finish up with a couple of slides relating to our patented algae system. And the first one is a fly-through. We can see each of these panels is enclosed, creating a gas duct delivering carbon dioxide and capturing oxygen from each panel. So you can see the curtains, on either side of a panel, directing that gas flow so the gases can then return back in the next panel and then down the next and back and down the next. Meanwhile, the algae medium is flowing from right to left. So now, if I go back to full view, there you go. There's only about 15 centimetre head difference between the far right of the marquee to the far left of the marquee, substantiated by Manning's equation. So not much energy is required to operate one of these algae growth marquees. This is a marquee, even though we are recirculating a lot of water. Also, this design allows us to manage the nitrogen uptake of the algae with injection of nitric acid into panels as required, or alternatively in the far panels, deprive the algae of nitrogen to produce enough stress to increase the amount of lipid oil content in the algae, a well-researched production enhancement method. Now, I just wanted to point out these light diffusion devices that capture surface light and deliver it deep into the panel. So the next slide shows the operation of these light diffusion devices. And these light diffusion devices are very interesting because they are separated by partitions, these partitions, forcing the algae medium to travel up and over a partition, and then down the light diffusion device to then travel up the other side, capturing the light along its path. And this cycle is repeated as the algae medium flows from right to left. Now, the light intensity in Northern Australia is 1700 micromoles of photons per square metre per second, whereas the optimum light intensity for algae is somewhere between 150 and 300 micromoles of photons per square metre per second, depending on the species of algae, which is 5 to 11 times less than what is applied from the sun. And thus, through this design, we can capture light and use it efficiently. We distribute that 1700 micromoles all the way down the light diffusion device. Now, light diffusion devices overcome the limitation of the 7 centimetres of light penetration limitation that would otherwise be the case at 1 gram of algae per litre, and also provides us with sufficient operating depth to maintain a constant temperature for the algae. So we're not reliant on the light striking the surface of the algae medium, as you see in many raceway systems. Now, these light diffusion devices contain purified water with pink pigment to reflect light into the algae medium. So if they appear pink, they are reflecting light. And though it may seem obvious, the spacing between devices and the partitions is commensurate with the algae design concentration. So a panel looks like this in cross-section, where the algae medium travels from one side to the other and into the next panel. A typical marquee, which I've just shown you in that fly-through, may have 11 to 13 panels, after which the algae medium is extracted and processed. Whereas the gases that travel down the gas duct must service the entire algae growth system, and which provide about 1,000 kilometres of ducting in which the gases are travelling at only 11 metres an hour for a fully dimensioned algae system, which accommodates 2,300 hectares of crop. See, the algae system is a farm in its own right, as is the sorghum farm. So you've got the algae system and farm, and you've got the sorghum farm. In other words, two farms that coexist with a production operation in the middle. And it's a closed system which allows us to manage, move, and utilise large volumes of gases. And then, of course, there's an efficient transfer of gases between the algae medium and the gas duct, relying on Henry's law through vertical water movement. up and down, up and down. I probably should also mention that we have a patented device that effectively scrapes the algae from the sides of the light diffusion device to keep it clean. Now, I mentioned earlier about our preference to produce bio-HDPE from the ethanol process stream, because there's a lot of extruded components required in the system, all of which constitute a value-add product for the marketplace. For example, HDPE sheet for farmers, farmers' dams, construction, and for mining corporations. And these are just some examples that will cause a manufacturing industry to develop as a result of our need to produce these components. As well as bio-HDPE, there's also a need to utilize bio-PET, that's polyethylene terephthalate, which is a clear plastic, good for light transmission, and which we can produce ourselves as well. Now, it might be a good time to answer any questions. And for those who are watching this offline, I have included my phone number at the bottom of the screen, or you can contact me through LinkedIn. And I thank you for your interest in what we have developed. Okay, so
thanks, Peter. Yeah, a lot going on there. Had a couple of questions come through, and I suppose one maybe is is this happening, production happening currently, or what's the sort of timeline on getting the system out there working?
We have a beta site operating, and we're working with Murdoch University on that. Mostly looking at our pre-treatment method, because that's a novel thing. We can always revert back to age-old pre-treatment, but we've got to examine these things that we believe, actually we know will work, and but we've got to prove it. And so Murdoch University is working with us on that. And yeah, we've look, there was we've only really, in the last couple of months, now that we've got all our patents settled, we've only really been able to go out to the marketplace and describe what we're doing, because it avoids the need for non-disclosure agreements, and allows us to talk very freely. So in this presentation, I've given you a lot of intellectual property, but that's all covered under our patents. And so we've only sort of got ourselves ready for that. But at the same time, we've been working under NDA with Murdoch Uni, and just proving up some of the processes. But all of these, the processes that we utilize are all, you can find them in scientific papers all over the place, but no one's put the picture together. They just looked at, possibilities and unrelated to, the total context. So we've, but what we've done is put together the total context.
Righto. So I suppose, just getting it out there more in market is a bit of uptake. Do you see what are the major hurdles, or how long before you sort of see it being implemented at a larger scale?
To take it to a larger scale makes it very easy, actually.
Right.
Because see, whether you go small scale or large scale, you're still going to need to extrude HDPE and manufacture the algae growth system constructed. And the best way to do that is with HDPE sheet, placing it down, make it waterproof, And so you're still going to need that, but that all becomes very doable when you're working at large scale, because it becomes, the capital cost of that becomes, it's not as significant as if you were to work at small scale. So when you're saying, let's do a small scale application, you've still got some large capital costs. But if you do a large scale, those capital costs, sort of disappear.
Right. Fair enough. So you'd be a space to watch to see how it progresses in the
it's very exciting
months
times.
And I suppose one of the points I suppose you made was the rainfall required was it 800 mils or so? Is that mean that it needs to be sort of the northern sort of parts of Australia?
A crop needs around about 700 to 760 millimeters of rainfall. Okay. But there's so when you're talking about but if you have a look at there's a patent that we've put in place that allows us to very effectively desalinate water for a crop. So we can be desalinating whilst you have the wet season, and storing that water in what we call our sump. Now, this sump is very effective because it captures all the runoff fertiliser that goes onto the crop, and this sump sits below the crop, right? And so it captures all that fertiliser, and then you can recirculate it, as well as the water that's captured. And so it makes, and that's the basis of that LinkedIn post that increases the production by 90% on the east coast of Australia. It extends from 2 crops to 3 crops, which is, getting another substantial percentage increase. And then, of course, we're basically relying on Queensland government studies in terms of the production increase in terms of utilising large amounts of fertiliser. So it's better to obviously the more rain you've got, you're going to be it's going to be much more affordable, much more profitable. And so the east coast of Australia looks very, very good for that. Up in Kununurra, there's no lack of water. So water is your limiting thing. But once you've got your 800 millimeters, you're ready to go. And you probably, so I put up a post a long time ago about working around the Gulf of Carpentaria. And so that relied on desalination. It's a post. So this whole thing about desalination hasn't gone away, but we're able to use it more effectively with this latest patent, which we put up on LinkedIn.
Right. Very good. Another question coming from Micah about how confident are you in meeting the design quantities of renewable diesel, and what does it take from a financial viewpoint to start a project? I suppose that depends on how big a project, but what's your...
Okay.
Yeah.
Thank you, Mike, for that question. For 2,300 hectares of sorghum farm, we expect to produce 28 kilolitres of renewable diesel, and from the ethanol train we will probably produce about 32 kilolitres of sap. Now, the renewable diesel is based on your algae growth, and the doubling rate of algae has been measured at 2.44 days for the Corella vulgaris algae. So it doubles every 2.44 days, implying that after 13.6 days, the duration of flow within the algae growth system, there's an increase in algae concentration of over 47 multiple. From the initial concentration of the seed, which is 0.29 grams per litre, to provide a final concentration of somewhere between 13 and 14 grams a litre. Now, this is far greater than our study's final design concentration of 1.47. So according to the doubling rate, we should get 14 or 13, 14 grams per litre. But we've only designed on 1.47 grams per litre. And thus we're using a highly conservative estimation of algae growth, which is the feedstock to our renewable diesel process. Now, the thing about, even though we could, if we had the carbon dioxide available to us, potentially produce at 13 to 14 grams per litre, the algae growth is limited by the amount of carbon dioxide feedstock that can be provided. And so, assuming that the carbon dioxide production quantity is correct, then the projected production of 28 kilolitres of renewable diesel is pretty much assured. I hope that answers your question, Micah.
So yeah, you're pretty confident of hitting those targets. I suppose, yeah, from the financials, what sort of dollars are required to set something like this up?
Yeah. Well, look, you're not going to get much change out of $90 million to get going. And so, it's you need a significant investor in this. But you don't want to go any smaller than that, because as I explained earlier, that you still got the capital cost, irrespective of whether you're trying to go small or large. So you may as well get your property and plant some sorghum, and then take it from there.
Right. No, sounds good. And there's one last question that Peter asked, about any biochar potential. Is there any connection in there? I suppose it sounds like you've got the system all pretty worked out, but we always get a question around biochar.
So the biochar?
Yeah, is there any benefits of having biochar involved in the system, or?
Well, you could make biochar. Because there's, I had a look at this about a year or two ago, and so I'm just trying to recollect my thoughts on that. But with biochar, there's the ability to break up your biomass, and which we do in the anaerobic digester. I think we thought that the anaerobic digester is a far cheaper way of going about it from a capital standpoint, and it's but mind you, with biochar you're pretty much processing all of your biomass, whereas with an anaerobic digester you're really only knocking over about, I think we use 63% of the biomass is converted into gases, leaving 37% of digester. But the digester is a good story anyway, because that's high value carbon, which you can bury below the crop. And so the carbon is not moving off site, which was one of the restrictions that was imposed on carbon farming. So the carbon's not moved off the site, but buried below the crop. And, you're talking about centimetres per year. In fact, I think for 100-year permanence, it works out to being about 30 to 40 centimetres of digested buried over underneath the crop. So you've increased the height of the crop by that much, but that's a 100-year permanency.
Okay. No, thanks. I think that sort of covered that question. But yeah, if anyone else has any other questions, please yell out. But I think probably just about wrap things up. But yeah, just want to say thanks for your time, Peter, and
Been a pleasure.
filling us in on technology, and good luck with it, sort of, getting some projects up and running. But yeah, thank you. And Zero Carbon Mine, we'll have more webinars coming up. We've got one planned for next month, still waiting on a few details, but stay tuned and we'll have a few more that we'll share you in the near future. But other than that, we'll leave it there. And no, thank you. Thanks everyone for coming along.
Yeah, thank you very much, Brett. Thank you, everyone.